All right, class, welcome back. Now we're going to talk about 3.3, graphing linear functions. The good thing is we have covered the majority of these topics already, and so we will be able to go through this pretty quickly, hopefully. Want to point out a few other things. So first thing I want to do is go through each of the methods that you can use to graph equations. The first method is point plotting. Point plotting is what I've done here. Okay, point plotting just means I'm going to choose a specific value for x, and then I'm going to substitute that into the equation. I'm going to say, well, when x is this, what is y? Or I'm going to choose a specific value for y and substitute that into the equation, then say, well, when y is this, what is x? Okay, so that's point plotting. Slope-intercept is when you solve the equation for y. When y is isolated and its coefficient is 1, then the slope is the coefficient of the x. This m here represents a slope. We'll go into this a little bit more in a minute. And of course this b here is our y-intercept, because if I were to plug in 0 right here for x, this would go away and y would be equal to b. So that would be my y-intercept. Okay, so we could also graph using intercepts, and the way we do that is same thing we do with point plotting, but instead of plugging in any number, I'm going to plug in 0, because 0, when x is 0, I'm on my y-axis, and when y is 0, I'm on my x-axis. So to find my y-intercept, I plug in 0 for x and see what y is, and to find my x-intercept, I plug in 0 for y and see what x is. Okay, so now back to graphing these equations. I've point plotted here. Since y is x, then I'm going to plug in -1, and because they're equal to each other, then I know that y is -1, and so on through here. Plugging in here, when x is -1, I'm going to substitute -1 right here, add the 2, and I get 1. When x is 0, 0 plus 2 is 2. When x is 1, 1 plus 2 is 3. So that is these two right here that we're going to graph. So the point -1, -1, 0, 1, 1. So this line looks like this. Okay, that is the y equals x line. All right, well, the y equals x plus 2 line is going to go through the point -1, 1, going to go through the point 0, 2, and the point 1, 3. So it is going to look just like this line, but let's make some observations about it. One observation might be that these lines are parallel. That's true. Another observation might be that this one doesn't have a b. If you're putting it in y equals mx plus b form, it doesn't have a b. Well, what's interesting about that is that's absolutely true. And that means that when there's no b, this line is going to go through the origin. It'll go through the point 0, 0, and that is going to be both your x and your y-intercept. But what's super interesting to notice here is that there's a shift. Every point on the blue line is shifted up 2 from the corresponding point on the black line. So that's what this does. When you add 2 on the outside here, that shifts the whole graph upward. Again, we'll talk about shifts later in the semester, but just kind of want to make some observations here about what we're seeing. Okay, for this next graph, if I plug in a -3/2, another thing is usually you plug in, like I said, -1, 0, 1, but here I chose -2, 0, 2. And the reason why is because whenever you have an equation that has a slope that is fractional, you want to plug in multiples of the denominator for your values. So for instance, 2, 4, 6, 8. Okay, so we want to plug in multiples of 2 so that they'll come out as whole numbers. If the denominator was 3, we would plug in multiples of 3. Okay, so when I plug in here, this 2 cancels with this 2, and I just get a -3 times a -1, which is 3. When I plug in 0, 0 times anything is 0, and when I plug in a 2 here, these cancel, and I just get -3. Okay, so the point here then is -2, 3, which is right here, the point 0, 0, and the point 2, -3. So this line looks like this. Using point plotting, I just put these together as ordered pairs. All right, so again, you can notice here that this equation has no b, which means that that goes through the origin like we talked about right here. It's going to go through the point 0, 0, and you can see that it indeed does. Okay, so what is this -4 then? If I tack this -4 on the end, what is it going to do? Well, -4 is going to shift every point on this line down 4, just like this +2 shifted it up 2. But you can see how that actually happens. When you plug in -2, you would get 3, and then when you subtract 4, then you would get a -1. If you plug in 0, you get 0. Subtract the 4, you get -4. Plug in 2, you get the -3. Subtract 4, and you get -7. So the ordered pairs here are -2, -1, 0, 1, 2, 3, 4, and 2, 1, 2, 3, 4, 5, 6, 7. So that is going to be like all the way down here. And again, what you'll notice is a couple of things. If I were a perfect drawer, then these lines would be parallel. True story. And all that's happened is they've just shifted upward or downward by this amount here, whatever this is. So we've shifted every one of these points down 4. Okay, so just a few observations, things I wanted to point out, so that when we talk about it later in the semester, it'll be familiar to you. And you can make your own observations here. The next thing I would like to do is talk about horizontal and vertical lines. Okay, horizontal and vertical lines are kind of unique in that when you're dealing with the XY coordinate system. So remember back when we were solving equations, it was like, oh, -2x is equal to 6, and if you divide by -2, this was like today, by the way, x is equal to a -3, and you're like, oh, I've got this. On this number line, this is the point -3, and it's like right here, and it's just this point in time. That's because this is a single variable, so we've got one variable here to the exponent of 1. Okay, so its exponent or degree is 1. All right, so what if I had the same thing, but I was trying to graph in the XY coordinate system? So we had this equation, but I'm like, no, I want this to be a two-dimensional graph. So then I get that x is equal to -3. Well, what are some ordered pairs where x is equal to -3? Or better yet, if x is always equal to -3, let's do a point plotting here. When x is -3, if I plug that in, 6 equals 6. Is there even a y there? There is no y here. So whatever x is, the y does not correspond to it. Like that, the x value doesn't change it. So this could be one ordered pair might be -3, 1. Another ordered pair might be -3, 0, and -3, 3. All of these have ordered pair of -3. So -3, 1 is right here, -3, 0, and -3, 3 is right here. So when you look at this line, when you connect these dots, you can see clearly that this is a vertical line. Okay, and the reason why is if I were to put this in standard form, remember back when we talked about the standard form, ax plus by is equal to c. Well, if the coefficient of this y right here is 0, then no matter what I plugged in here, so if this says -2x plus a 0y is equal to 6. So I'm just rewriting this equation in this standard form. But because there's no y in this equation, we know that the coefficient was 0. So now I can try plugging this in, and you could see a lot easier that 0 times anything just makes this 0. Okay, so 6 equals 6, this is a true statement. So the reason why we can get multiple different y points is because the coefficient of this y term is 0, essentially, is what's happening here. So how did it get from a single point to a line? Well, here we're dealing with one variable, one exponent, and so are we here, or so it seems. But if you're graphing in a two-dimensional system, there has to be y values. So the y values can be anything, but no matter what they are, this says that no matter what, x is always -3. So here are 3 ordered pairs where x is always -3. So what you need to remember is that a vertical line is x equals some number. A just means some number. And this slope is undefined. We'll get more into that in the next lesson.